No, I think,
Five. Yeah.
well, good afternoon, and many are here from different parts of the bus community. I am retired, and I come very much from the land, resources, ecosystems, where I sort of got entangled in dust for a while. It was lots of fun, and I'll tell you a little bit about it. One thing that needs to be stated quite clearly is that Icelandic ecosystems are so heavily influenced by dust that it's surprising. All of the systems are much more so than most other ecosystems in the world. The soils and everything form in dust. And to come back to that a little bit, so the dust is depositing at different rates depending on where you are in the country. So the surface is gradually rising. There's vegetation on top of the surface and capturing the dust. And this dust is not stable by any means. It weathers quite rapidly, forming clay minerals, accumulating carbon, and doing weird things, and creating very special properties. And these properties are called anti-soil properties, and this is a special order in all the major classification systems in the world. But the Icelandic soils are in many ways unique. So we start from the glacier left there, the land, and it's been rising steadily. Sometimes we have big volcanic eruptions that produce tephra, volcanic ash, that can be dated, so it's kind of nice to go through the profiles and you know where you are in time. And that means we can also calculate deposition rates very easily. But the geologists in the older times, they made huge mistakes in these calculations because they thought there were no chemical weathering in Icelandic soils, which is nonsense. And so a lot has been lost. So this is not showing all the material that have been deposited. They've been converted to aluminum, allophane, ferrite. A lot of things have been lost. So I come from the soils and also come from the soil erosion mapping. A lot of controversy about the soil erosion in Iceland for the longest time. Was it a problem or not? So I got this beautiful job to map soil erosion in Iceland, and it took us 8 years. There was a group of us every summer. So I was paid per diem to travel in Iceland and hike summer long for 7 years. It was a beautiful job. And we gathered huge amount of data. And we sorted the erosion and the deserts, the barren areas were special entity of the system. And so we came up with a unique data, the geographic data of the deserts in Iceland, and also I've been everywhere. I've seen, I saw where the dust was coming from and so forth. There were satellite images of the dust plumes were not available when we started out. And we had to sort the deserts into several categories, like the sand field, the gravelly, black gravel surfaces, and more gravel surfaces, is the next one. The lava, sandy lava surfaces, and so forth. On all of these surfaces, they behave differently in wind situations, and the texture dominates and dictates whether it's dust generated or not. So there are a lot of complicated factors that govern. But here's a map that we took out of this database showing the sandy deserts. And we found out that sandy deserts in Iceland were about 20% of Iceland. about 30,000 square kilometers, depending on how you define it. This most severe erosion were the red areas shown on the map below. And they vary from place to place. I mean, there is the gravelly surfaces and then sandy, gravelly surfaces like this. And in high wind situations with 25 meters per second or more, all of these surfaces become unstable and they produce dust. But still, they're not the major dust source today. And that came as a surprise, really. So the sandy, gravelly surfaces are the most common of them. But the sand fields are behaving differently, and some of them produce a lot of the dust. But they are about 6,000 square kilometers today. That's a lot, actually. But we knew that the dust was actually not coming from all these deserts except in very high wind situations. And some of these areas were almost a constant source of dust. And we defined these areas on the map here. I will show pictures of some of these. And when we started to get notice images, satellite images showing the dust flows, the picture came quite clear. But these were the main sources of the dust. Even though all the other sandy deserts could produce dust. And as a byproduct, it was not my main interest, but I published a paper in 2010, sort of explaining what I've done so far, and that we had a very dusty area, and there was a lot of dust being deposited in Iceland. And this was right before the volcanic eruption of Eyjafjallajökull, and all of a sudden this paper became sort of important. And it became the highest cited paper in this obscure journal, but it's available on the net, so it doesn't matter, it's quite available. And then, but people sort of didn't quite get it. It's not important, and there were a lot of confusion about this. Is it so dusty? Then the ecologist measuring the iron contents in mosses, they had seen some very strange distribution of the iron in the mosses. And really what they did was reproduce the map. So our map explained their data. And the FlaxPart modeling from that time was not doing quite well because they missed the dust sources, the dust hotspots. And then this lady came along and we started to work together. She took a PhD and she did postdoc and she established all sorts of networks and she traveled around the world and she's been doing quite well. And especially when I was participating in this until about like 2018, we were hyperactive actually. We published a lot in cooperation with a lot of different people. And then we decided sort of simulate or make a review paper of the Icelandic environments. This is in the Alien research. So if you're interested on it, but this is a open resource paper. And back to these major dust sources. The old geologists, they believed that this thickening of Icelandic soils did not come from wind erosion from the desert. It was more like coming from the area around it. It was published in the major geology books up to the time. So I had time actually publishing this and saying, "Oh, this is coming from distant sources," and they were arguments about this. But we sort of settled all these arguments. I think people now are in one line what is happening. And now we'll talk a little bit more about this different pictures from Hagavat and Thinking Center and all these different sources that we have identified. And what is happening, we've seen this from Greenland and so forth, so it's the same story. We have these glacial rivers carrying out, and the numbers are in millions of tons of loose sediments. We also have old lake bottoms that used to be glacial lakes. And then the ocean fronts, the rivers bring out more of sandy materials. There is a sorting going on in a lot of the finds are actually redeposited on the ocean beaches and become hyper sources of dust as well. And then numbers for this is just staggering, how much material is involved. And imagine this is Mýrdalsjökull in South Iceland, and this river comes out there, and sometimes gets all the way down here, but it just disappears, more or less, in most days. The water just doesn't make it all the way into the major river Drenginyera. The sediments are left on the surface, just like we saw in the movie from Greenland. But this is a lot that is being carried. And there are daily flights. Driving over this is actually adventurous. And it gets really stuck in this. This is Pavla's favorite tiki center. And there have been a lot of equipment being put out on tiki center. And you see the major river coming, but it doesn't make it yet. But it did sometimes, and they had to remove all of their instruments way down this channel in 2022, right? 21, yeah. But the sediment load of these rivers are in millions of tons. So there's a lot of material available. And it doesn't take much to start moving. And the light color is because if you have a lot of silt and you get it small and large, the color refraction, the light refraction changes into lighter colors. And if you have more coarse sand and stuff, more light colors, fine silty material, it becomes lighter color, even though it's all black and opaque under the microscope. And then we have these outbursts from hot spring areas under glaciers and glacial outbursts from called jökulhlaups. And there's just a lot of materials that are brought down. And this is a famous photo actually, often been shown. This one, there's a lot that is being blown in the major storms because we get these immense parabolic winds from the glaciers with the low pressure hurricane being added to the glacial effect, the wind speed can be enormous. So we have hundreds of thousands of tons of materials blown each day during these storms. It's a lot. And here's a proof that the arrow follows. It's a river of sand, really. That is what happens in these areas. And so the sand is being blown from the sources, even tens of kilometers, and accumulates somewhere where the wind speed is reduced due to geographical change. We have some mountains or hills to stop. So you accumulate the sand down here. And this has happened in this area just over the last 200-300 years. This is our was favorite, this is my favorite, and this is Thinking Center dust source. The reds here are the source area being blown from south westerly to southeasterly winds. Those are the dry winds. more or less over half of the country from this major source. But water takes back some of the sun. So it's a sort of a circular thing, comes and goes. And we're a little bit of sun here. And you start with very fine material, and you end up with relatively coarse material up here, and less dust, because it's lost with the ocean. This is how some of these areas look on the surface. I like this because it has the polygons that form a mixture. It reminds me of Death Valley in the US. If somebody has been there, there are some salt flats with beautiful polygons. This is the silky material. Here they actually want to build a dam and try to sink this. Where this was actually created under a natural lake, natural dam. And I have no idea why they want to create a new problem. The best thing to do it is that this globe takes about 50 more years. And the problem is solved. But they will create a much bigger problem if they try to sink this. And here, this is looking out the window here. And we are about 75 kilometers from this dust source. And this is on a windy day with easterly winds, a lot of dust. And this is happening over and over again. So when you accumulate this over thousands of years, you have the soils. We tried to estimate how much this dust is. And we came up with two numbers, 30 million tons based on counting dust storms and trying to give the values. And then metadata for soils in Iceland, which gave 40 million tons. So that was the estimate that we published in a paper in 2014, and we tried to extend this to the oceans. So this dust is full of iron. Icelandic dust is 10% iron. The primary conductivity in Icelandic seawaters is mostly limited by iron. So this probably has a huge impact, but it's still an open question. That's kind of hard to investigate, actually. It becomes very complicated. But then some have been modeling using older models, not new models, and they come up with way lower numbers than we got. But I think with the more recent models, actually, this is probably going to be more or less the number. But as I said, it's complicated because some of these other areas, not the dust hotspots, in addition to the dust hotspots, they emit in high intensity storms. This is a map again of the distribution, and we'll make it a little bit nicer and more categories. And this is in grams per square meter per year, and having up to 1 kilo per square meter per year, that is huge. We have a very dusty land. And one thing that I think the models may do better job of is to account for redistribution. This dust settles mostly closer to the dust hotspots, but they're not stable. They're remobilized, as we saw so much after Eyjafjallajökull volcanic eruption. So I think there is a room to improve the models for resuspension. So, as I said, this is affecting the weathering. This basaltic volcanic acid weathers extremely rapidly and creates new clays, allophane and perihydrate mainly, and these are very active, very tiny clays. And it keeps the pH high in the soil because basalt basic, acid basic that's drawn from the term basalt in rock. So basalt weathering pushes the pH up. And this material, allophane and perihydrate and others, are created by weathering of these materials, accumulate carbon. So there's more carbon in Icelandic soils than anywhere else in Europe. Iceland wetlands, heat in Finland and so forth, you would think they have much more carbon than here. No, there is an equal amount of more in Icelandic wetlands. They have much lower percentage, but they're heavy because of the basalt. When you multiply the rock density by the percent carbon, then you get a high one. Each square cubic meter of this stuff is so heavy, even though carbon content is low, there is so much weight in it. So, and I could go forever, but all this unique, and I said, I have the last here. So, and birds are sitting on the top of the nutrient chain or food chain in like Iceland. And there are unique data sets on bird density in Iceland that people could not figure out what was the reason for this strange distribution until they combined the data. And bingo, what explains the fertility of Icelandic soils is, and ecosystems, bird density is the dust. More dust, the more bird seed. It's not vice versa. Dust is good for this. So whether we should do something with these dust hotspots because there's some terrible pollution from many parts of Europe, it's an open question. It's going to be very difficult, and many of them are within national parks, and it's actually forbidden by law to do something. But so that is for future generations to deal with. I think I'll just.
Thanks a lot, Polly. Heard several similar stories from you, but still there are some new things that I would like to discuss with you a bit later.
Okay.
One of the things I just reserved, since I'm conducting this session, you show one of the map already published where there is a pattern over the near sea where the position of iron together with the particles exists. Is there any measurements of the biological activity in the marine of this area?
Yeah, there have been attempts, mostly from Germany, to try to look at the bioavailability of this. But I think, and it's expensive. You need you ship big ships and resources and so forth. Okay. But I think there's ongoing research.
Okay. My question is because my group also have one reference this modeling, where over the Atlantic Ocean we try to compare our simulated biological activities of planktons with some ship measurements, but it was too few data to really get.
That sounds like excellent.
Sorry, I exploited the fact that I was sharing. The next questions, please, if there is any. If not, thanks again.
And I was
Very nice.
if I can only innovate a little bit, so because as the Ice Dust Association, we have something for you too.
Oh.
So yeah, you've been standing at the beginning and helping to establish the association which is running. And there is a dust print of you made by Beata again. So it's the new Sandu you were showing. Problem. So
Yeah.
I keep the third one. I hope I can get signature.
Right.
Any questions from the audience, which is not in our conference call? Have any question?
No, not
No.
in the, not in the.
Okay. So the next presenter is Slobodan Mičković. Can you help open the
Thank you, Onichko. I know it's not best to introduce yourself in your
That's
own
okay.
session. I think that's- No, hello. And the presentation.
Yes, that's right.
And hi, this is okay, we will record it still, right?
Yeah, for sure.
And share screen. Good morning. Like this.
Okay,
Thank
thanks a
you.
lot. So, as you can see, a dream model island Atlantic the model. This is modeling study that we start to perform sometimes ago, still ongoing, and is addressed to glacial darkening by dust. You already heard some comments about that. That's obvious that one of the environmental impact of dust is deposition on the white surfaces and then changing the radiation properties of the earth and especially of the snow and ice. So this kind of our novel approach simultaneously predict the transport of dust, what we are doing anyway in our models, but also we are trying to add also transport of dust darkness or dust color. So this means that we would like to have in our model all the cycle from emission to the deposition of dust, but also to add the color of dust into the whole story. And darkness, which is 1 minus albedo, simple relationship, is basically physical property carried by some material, by some mass of dust. So, talking about the problem of influence of dust to the control my time. IPCC declared that dust is a short-lived climate forcer, which also, among other things, contributes to glacier melting. This was recognized by the international community. Definitely. Dust deposited on glaciers means absorption of the solar radiation, means then accelerating of the melting of white cold surfaces. So this is the chain that we would like somehow to introduce into our model. The melt depends on two things: on the amount of dust deposited on glaciers, is one thing, and on dust color. And the first one we have in different models, including ours, but the other one does not include dust albedo or color, like as a prognostic variable. So in this way, in current models, as far as I know, there is no prediction of cryospheric darkening directly in the prognostic mode and corresponding melt of that. So, talking about darkness of the dust, definitely Icelandic, as we learned from Oli's presentation, this is very dark because of the specific mineralogy. Iron is there and other factors that really make it dark. And you can compare how in satellite images on the left, this is albedo, surface albedo in Iceland. The second image shows Saharan surface albedo, and you can recognize what is the big difference. I mean, in Sahara, this is much lighter dust over there. So, how we perform our intention or our concept to introduce the color of the dust? First, we started from dust sources on the top left. This is just image showing what you can see on a satellite data. I mean, satellites today in a very high resolution make available albedo on a daily basis or even shorter, in a minute basis or so. This was one data source that we needed for our work. And then out of that, we calculated the soil albedo on the ground. And then from our Dream Iceland model, we have another set grid data, and these are the sources. So we basically make intersection of dust sources with a map of soil albedo in the same grid points, and then as a result, this is colored values of sources on the right. And this was our basic, how to say, data in the model. When we emit some dust, we don't emit only particles with some particular mass, but also we emit its color. And here you can see two maps. On the left, this is darkness of source maps, how the model see it. The model is about 3.5 or so kilometers grid distance, grid resolution. And on the right, this is dust hotspots. Thanks to Oli and Pavla, years ago, we introduced this data into our model. And so you can see that, I mean, if you carefully look, every hotspot or every source in the island, you can find its darkness or color on the left-hand side, thanks to Juan Zvetkovic, who made the effort to really go almost point by point, controlling if our data are consistent with the data sets. So, the next, we learned from the, how to say, fluid dynamics theory that there are so-called intensive physical properties carried by some mass. So, these examples of intensive properties are color, odor, energy, temperature, pressure, and all these parameters does not depend on the mass or on the mass that carries them. To make this process consistent or to make available that we also transport material together with a color or with some other property, we multiply the variable with some concentration. In our case, on the equation on the bottom, we introduce so-called specific darkness. Not only darkness, as the first equation shows, but specific. So this means that we have a multiplication of concentration, dust emitted and transported, but also its color. It goes together as one parameter. And this is actually what has been done in hydrodynamics, and on the right-hand side, we will not go into the equation, but this is on the left example how in atmospheric models, this is introduction of specific heat. Heat multiplied by density of the air that transfers the heat. And on the right-hand side, this is complete analogy. In our case, this is the equation of what we are going to do, introduce into the model. And this specific C is concentration, D is darkness. And once we did it, we ran the model now with a new equation. And there is a strong darkening case of 2002 in July, and glacier is Vatna Jokul. And this is how it looks like when you look before this particular date on the left. This glacier is very white, but then once it was a very strong dust storm, right, you can see the gray part, which is the result of deposited dust. So we ran the model over 1 week, a day before the event and several days after. We are not going to go into details of these maps on the left, but you can see evolution of the system for different time steps over this period. And you can see the arrows. The long arrow points out that in the morning hours of 7th August, there was some deposition and also surface concentration of dust. This was dust storm. Then at the same location, or nearby, we have this large glacier, and on the bottom left, you can see how it looks like several days after. So it was deposit of the dust, and then the darkening of it remained for some, I think about 10 days. Maybe the new snow came and covered it. So this was perfect case for us to test the model. And just on the 7th August, this on the left, the image shows every 3 hours how the darkness that we predict starts to grow up. So this means this was surface value, and from 0, it started to increase all over the day. And then on the right, this is the graphical scale is for 1 week or 10 days or so. And you can see that between 7th and 8th, it was strong peak, indicated the activity close to the surface because of the dust presence. And it was almost my artistic effort to try to draw something on the maps. I used the same scale of the glacier on both cases, and then I was trying to see how close our prediction was when we compared with the satellite image showing the situation of the glaciers. And you can see on the bottom left, there is a structure like here, similar to what was observed, but also there are some few other components of our simulation that I would say are not far away from what was observed by the satellite. On the bottom right map or graph, there is in one of the points of the glaciers, there is an observation station, and this was clear that the drop was also recorded just on 7th of August this particular year. So it seems that we are probably on a good way to somehow close the story. It will not be only one case, but we really plan to even start running it on a daily basis together with our daily forecast that we provide anyway. So it would be really quite interesting to see for the new cases how this new component of the model performs. Thank you very much.
Michko, so I don't know, are there any questions in the room for Michko? Do you have also maybe some estimates how much melt it can cause? Or if
I didn't mention this one, but you opened basically another question. In our prognostic system, I mean, we can run it over a year, for example, to make a kind of climate study with the same model. But in our case, we don't have adequate surface soil scheme. There is some, but it was not the scheme. The soil scheme is not very much adjusted to this new information.
Yeah.
So my colleague Anna Vukovic, she was doing, I think, for her not graduate but postgraduate thesis, this kind of study. So there is offline model of that kind, but now we are thinking maybe to include this more sophisticated surface scheme and connect it together with the new parameters that we are having in the atmosphere. So this is just a plan.
And we have some questions in, yes, Santiago, please, so then you raise your
Yes.
question.
Yeah. Okay. Hello, can you hear me?
Yes,
Yes.
we can.
Okay. Hello here from the other side. Regarding this presentation, I'm curious about your definition of darkness. Maybe I missed it, but the concept of darkness is because it's an optical property, you're dealing with intensive properties like composition and particle size, and more extensive properties, which in this case I would say is number concentration and thickness, because it's how much is deposited on top. So maybe I missed it or you mentioned, but how do you account for both? Because you can have a very light dark material, but if you have a lot of it, the optical effect is the same. So do you account for both effects?
Yeah, actually, if you look at this parameter that I was showing in one moment, C times D, this is specific darkness, which includes the concentration, the amount of mass, and also the albedo, if you like. Maybe that's easier to somehow accept the point of albedo rather than the darkness. But if we also have the equation only for darkness, not mixed up with the mass. So that's another equation that is not independent completely, but as a single prognostic equation for that one. I understand your point. I hope that if you have a lot of dust, which is, let's say, white, it will be white, right? But if there is some color different from zero for albedo, in that case you can combine the mass and its color. I'm not quite sure if I
no, we can follow up, but I get the idea. Yeah.
Okay.
Thank you. And is there any other question online, please?
Well, I asked a question to both. I put it there in the chat for both of the speakers. I guess, but we can do it at the end because it seems like a general question to the speakers.
Okay.
Yeah, it will be, I think, at the end.
Yeah, we can have an open discussions, yes. All right, so if nobody wants to raise the question straight away, because I'm not sure from the chat here, so we proceed to the next speaker, and there is a change now, so.
Okay. So the next presentation is my colleague from Belgrade, Dragana Đorđević, Professor Đorđević, and well, let me find your presentation.
At the last page, sorry, but you might miss the page because we have changed it from the, sorry, that's my fault here, I did not
No
get
problem.
this one, like carbon.
Yes, black carbon in the atmosphere of Belgrade, Serbia.
Should we check the green first?
Oh, Dragan, the floor is yours.
Yeah, she did, but we tried. No, sometimes it's okay. Okay, thank you. Maybe they're gonna also start with your connection to the north, and why we have also.
I will try.
That would be good for that people. Thank you.
Good afternoon, everybody. I'm going to speak about different type of dust. This dust is from carbon, and black carbon is generating in combustion processes, anthropogenic and natural. Carbon is widely distributed element in the environment. And this component of black carbon, anthropogenic sources can be separated into two categories. Combustion of liquid fossil fuels and combustion of solid fuels such as wood and coal, mainly used for the rest of the heating industry. Black carbon also is settled globally in ocean and by dry and deposition. Black carbon absorb solar radiation and transform it in the heat. Influence on human health, on climate, and air quality, etc. Biomass burning emissions could be from forests, from harvest fires in anthropogenic activities, and from domestic heating and cooking using wood.
It's kind of cutlery,
Oh.
right? So is it okay? We will just jump out of the
Okay.
presentation mode where it's pointing. So we will just present it like this because the
Okay. Okay.
parameters.
It's
I
better.
hope it's okay.
It's better. In many European countries, wood burning makes big problems to increase PM2.5 concentration, which involve new European directives. In urban areas, traffic is main sources of black carbon. In the last decade, in our country, in Serbia, air quality became very bad. Became also alarmingly poor. Sometimes during winter periods, became the worst in the world. What is this reason? It's coming a lot of foreign investors with dirty technologies like smelters or steel factories, firstly from China. There's factories producing for global needs, and because of that, they need a lot of energy, a lot of energens. So Serbia is a small country, there is not enough energy, and starts to import a lot of waste materials like waste rubbers or waste plastics. And this is reason why air quality became very bad in Serbia. We measured 7 months in high time resolution of PC, black carbon, divided to black carbon coming from biomass burning and black carbon coming to fossil fuel. Our measurement station was in the city center of Belgrade. First results shows this is time distribution of total BC and BC from biomass burning and BC from fossil fuel. On the right side, you can see frequencies of the concentration that we measures in this period. This picture shows the percentage share of black carbon from biomass burning in the total black carbon. And you can see that in non-heating period, this share could be about maximum 20 with with several outliers, 20%, but in the heating season, this share could be reached almost 70%. The reason is because in domestic heating is using huge quantity of wood. Distribution per days of these three types of black carbon shows in the first column. You can see that during nighttime, the concentration of black carbon are the highest. But in rush hour, we have increasing in the morning and in the afternoon also we can see increasing of black carbon. During weeks, the lowest concentration of total black carbons are in Sunday, while black carbon originating from biomass burning is the highest in Sunday because this day people are in their houses and heating their houses using black carbon, using wood. And the lowest concentration of black carbon from fossil fuel is on Sunday because many factories don't work on Sunday. This is correlations, but I will leave it to Sofia tomorrow to explain you much better, my young collaborator. But I will show you principal component analysis, which found three factors. First factor is combustion products. Second one is combustion products from incomplete combustion. You can see that is connected with wood burning, biomass burning, PM2 also, and CO, which is indicator of incomplete combustion, and in anticorrelation temperature is if is lower temperature, much more burning biomass. And second one, originating from atmospheric chemistry, CO2 transformed to sulfates. Ozone is generating with VCO and nitrogen oxide, etc. And we compared our result with other European cities. The lowest concentration is in Stockholm, but the highest that is surprised us is in Milano, in Italy. Milano is the city of European country, but they have much higher concentration than in Belgrade, which is the most polluted in its history in this time. I'm coming to Reykjavik many years, and this time I noticed that air pollution increased. I surprised about it, and it surprised me that your mountains are without snow almost. That means that this glacier are melting fastly. That's all. This is first our results. Thank you very much.
Thank you, Dragan. It's quite interesting
Um,
to know
different.
who is suffering a lot. A lot.
Yeah.
Okay, so I would like just to ask, this is so strange and
Yes.
unexpected.
Yes. Yes. Also, I'm following the application Ventusky,
Yes.
and often I could see fumes from Milano, which pass through the Adriatic Sea.
I
To
see.
the
So it seems that this
I don't know what is happening in
yeah,
Milan.
that's so strange.
Yeah.
But anyway, questions for Dragana? Yes, please.
I wonder if the Milan enhancement has any dynamic confinement effects from being blocked by the Alps. That's something to look into that.
Sir?
Have you looked into the dynamic blocking by the Alps?
Maybe orography of terrain is different, and maybe Nichko could knows better than me. Because
Yes, topography is one of the.
But Belgrade is open and has very good ventilation, very good winds.
No high
Sources.
Mhm.
mountains
Yeah.
around.
Despite two strong sources, wind carrying to the Europe.
Okay, any other question for Georgic?
It's one online, Daniel.
Now, can you help me? There is an online question.
Maybe. Just the online followers can just, raise their hands and just speak up. Or I'm from Milan, Biagio di Mauro. So Biagio, we'd like to hear you. Can you say it?
Oh, okay. Everyone.
Hello.
Oh, we can hear you. Nice to.
Yeah. It was just a comment from my side. Hello, everyone. Since I'm here in Milan, I was just confirming that the air is quite crappy because of multiple processes happening here. The Alps are blocking air mass transfer, and we also have a strong pollution sources like big cities like Milan, Turin are in the Po plain. So that explains a little bit your graph.
Okay.
Thank you.
Okay.
Thank you, Biagio.
Okay,
Maybe if I can also add, I think the latest report, I'm not sure if that was the Environmental Agency of Europe, but the actually highest mortality from the air pollution comes from the fine particulates PM 2.5. And for Europe, the country with the highest mortality due to air pollution, it is Italy.
Really?
And it's the Po Valley. So although Balkan countries are known for the worst air quality, I think North Macedonia is the
Yes,
winner,
yes,
Skopje.
Yes.
But, and yeah, this pollution.
Bosnia also.
Yeah, but from the numbers, it is Italy. And the long range transport towards
Yes.
the Arctic, it's so poorly known, but it's obvious that something is happening. Yeah, and maybe I would ask Dragana because she has also connection to studies on the aerosols in the Arctic and transport from the Arctic to Europe. If you would say something.
Yes, we published some article together from the dust from Iceland. We found that about 3% of situation coming to Serbia dust emitted from Iceland.
Yeah, I mean, that's one of the longest range transports.
Yes.
Over 3,000 kilometers, if I'm correct.
Yeah.
And
Yes.
3%, like weather situation, it's quite a high number. So earlier today, OT was showing graph of long range transport, for example, from Aral Sea dust towards Finland or Saharan dust to Finland. So that's the other way when the high latitude dust is reaching Europe. So obviously not many studies from continental Europe itself, central or western, but it is all the way from Balkan Peninsula, found on the roof of your institute. Yeah, so that's just the connection also why Dragana is always very welcome on the high latitude as workshop as everybody. But okay, thank you.
Papa.
Thanks, Dragan.
Thank you.
So, coming to the last presentation, right? For this session, and this is Dr. Susan Kasperi from the USA. I hope she's online.
Hello, Suzanne, we can see you.
Okay, wonderful. Hello, everybody. Thank you for having me. Let me get this projected. Are you able to see it okay?
Well, the bottom is slightly missing, but I think it's only one line, so it should be okay. If you can maybe show the second slide, if it's, yeah, like maybe small part of the bottom is missing, but I think it's gonna be okay.
Okay, we'll go with that. Well, it's nice to be with all of you. I was able to attend the workshop a few years ago and got a lot out of it. So I'm happy to be able to attend remotely today. So this is work that I've been doing since 2022, predominantly in collaboration with my Norwegian colleagues, but with several others as well. And so some of the earlier speakers have already provided a good basis for this. So as you all know, we're interested in dust, but much of the Arctic is covered by extensive snow and ice cover. Let me just shrink the speakers. And so what I'm particularly interested in is light absorbing particles that get deposited on the snow and ice surfaces that can then darken the surface and reduce albedo, which you already heard about earlier today. So this can produce feedback loops where we end up with accelerated melt that then exposes more dust surfaces, which can further enhance energy absorption and warming. And we saw in one of the earlier talks in this session how important glacier environments are for this. And so as we have this changing environment with further glacier retreat, we're expected to expose even larger areas of dust. And this is going to result in then even more dust that could potentially get deposited onto the glaciers. And so we've seen recent work by several people, including those that are here today, that have made increasing calls to have a thorough assessment of how climate change is both influencing dust emissions and their interactions with the cryosphere in the Arctic. So as you know, the Arctic is warming, and that those bottom maps there show that it's not warming equally everywhere. We know that that we have faster warming in some regions, and Svalbard is in that hot spot of warming areas. And so it's been estimated that warming on Svalbard is as much as 7 times faster than the global average. And so this is just a map with the red areas showing where we have particularly fast snow and ice melt on Svalbard. And so that warming is an important part of that. But a lesser studied part of that has been the deposition of the dust and light absorbing particles that darken those snow and ice surfaces and accelerate melt. And so up until recently, the majority of the work that was done on Svalbard had focused on black carbon, but little has been known about dust deposition. And so the objectives of the work that I've been doing with my collaborators is to look at the spatial and temporal variability of dust deposition onto Svalbard glaciers and what's driving the dust deposition, look at the differences in the sources of dust that are deposited on the glaciers, assess the contribution of dust and other light absorbing particles to snow and glacier melt processes, and then investigate recent trends in dust deposition onto Svalbard glaciers. And so this point was made a couple of talks ago, but how absorptive different particles is dependent upon the composition of the particles. So these are the main light absorbing particles that we tend to study, with the right showing that very, very dark ash that's found in Iceland. And these are just showing different numbers of the mass absorption cross section. And so up on the top left, we see that black carbon has a very high level at 7.5, whereas the absorption efficiency of dust is highly variable depending upon its mineral composition. But this slide, the main point here is just that a lot of the work is really focused on black carbon because it's so much more absorptive and has many human sources. But if there's a lot of dust in the environment, then dust really needs to be what we're focusing on. And so past light absorbing particle research in Svalbard has predominantly focused on elemental carbon and black carbon. Dust has received less attention. And so of the dust work that has been done on the glaciers, a lot of it's been done in the ablation zone, which is less representative of the large sweeps of snow-covered areas that exist for much of the year. And there's been no information really available, with the exception of the study from Cavan that shows how much dust is actually, the dust concentration is actually in the snow. But these studies were done more so in like Gugoli environments on the periphery of the larger, more extensively glaciated areas. So we've really had a big gap in our knowledge about how much dust is actually getting deposited on this area of Svalbard that is very extensive in both glaciation and then also seasonal snow extent. These are a couple of pictures just showing how dusty it can get. And so the dust storms tend to happen during the late summer going into early fall, when much of the seasonal snow cover has been removed. And so depending upon the kind of heating and cooling processes and how wet it is, will depend upon how much dust can actually get lofted up to higher elevations. But so these very active dust valleys can definitely be large dust sources. And then also just regional rocky outcrops can also be important. So since 2022, I've been working with my colleagues at the University Center in Svalbard and with the Norwegian Polar Institute to collect snow and ice cores from around Svalbard. So today I'll be presenting the results that are predominantly from Holtadelfana, Kongsveien, a number of glaciers out on the peninsula by Ny-Ålesund, and then Dranbreen Glacier. Last year, we also sampled at Elfenbeinbreen and Philippbreen, and this spring we're planning to go back and are hoping to be able to sample at Lomonasafana and at Edvardbrain. And this map on the right is just to highlight that these sites are coming from geologically diverse areas, and that some of these are coming from areas that have more extensive glaciation, whereas some of these have been collected from areas where there's much more large exposed areas of dust, and they're very close to large valleys that have a lot of dust sources in them. So our methods, most of this work has happened in the springtime. On the left here is showing snow samples that was helicopter supported, but most of the time we're accessing these sites by snowmobile. So most of this work has been done by collecting shallow cores with a Kovacs drill, as you see in the right two images. Our methods have been to just isolate the dust using gravimetric filtration. Some of these sites have quite low dust concentration, so the amount of snow and ice that's required to actually get enough dust particles to study has required large samples. And then we've been looking at the mineralogy and the composition of the dust via X-ray diffraction and scanning electron microscopy. And then we measure the black carbon using a single particle soot photometer. So there's three main areas of results that I'll share with you today. The first is getting those first measurements of dust concentrations and dust deposition. So prior to this work, we really had no idea how much dust was actually getting deposited up onto the extensive glaciers and ice caps of Svalbard. And then we're looking at dust composition and then looking at what the relative albedo reductions are from the light absorbing particles. So this is just showing Svalbard winter snow particle concentrations. And for a lot of these sites, we're limited to being able to measure in winter snow because there's so much warming happening on Svalbard that there's a lot of areas that no longer have any fern remaining at the end of the summer season. And so what we would do is go into these glaciers and at the springtime and drill down and collect the snowpack that goes down to last year's glacier surface. And then from that is where we would get these winter snow particle concentrations. And so the concentrations of dust in the winter snow are quite low. And this isn't ultimately what we're truly interested in because for much of this period of time, it's dark there, and so there's not sunlight exposure, so the albedo effects aren't so interesting. But the concentrations that we're measuring in April still give us some indication of what kind of concentrations can be exposed at those glacier surfaces as we get into the long summer days when there is a lot of solar activity and albedo becomes very important. So this is the winter snow particle concentrations. And then we also look at particle deposition. So this is then a metric of looking at how many milligrams of dust per, oh, that says grams squared. That should be meters squared there on that left axis there. But this gives us then a measure of how much dust is actually getting deposited. And so for most of these sites, once again, we are only able to get winter measurements, but from a few of these sites, we're able to get summer measurements. And so these are from the sites that do retain fern through the summer season. And so we get that summer concentrations are much, much higher than what we get during the winter time, as we see over here during the top right. And so this once again is because we removing that winter snow cap that covers much of Svalbard, and then those dust sources become exposed and can become activated. So this is Biagio, who's on the call, I believe, today. He did a nice review a few years ago that synthesized some of the measurements that are available from elsewhere around Svalbard. Some of this is in very active glacial valleys that have a large amount of dust being moved and reworked. So there's some areas where we have much, much higher dust deposition. But if you look at the concentrations that we have relative to what Cavan has at the very bottom there, we see that what we are observing on the glaciers can actually end up being more than what has been seen in those gullies from the work that was available previously. So we're interested also in looking at how this changes over time. So this is a fern core on the right showing winter snow on the left side of the picture, and then the right side is showing that exposed fern layer that would have been at the surface during the prior summer. And so very high amounts of dust, and you can also see the melt that is very apparent that dust, that presence of that dust caused on the glacier. And so what we want to be able to do is use these shallow fern cores to be able to reconstruct how much dust has been being deposited over time and to be able to look at differences in conditions from year to year and to the factors that might be driving interannual variability in dust deposition. But what we consistently observe is that the last year's prior summer layer will always have the highest amount of dust deposition. So on the top here is a core that we collected in 2023, and on the bottom is a core that we collected in 2025. And this is just showing that in both cases, we have this very, very high dust layer that exists in the last year's summer fern. So this would have been at the end of summer or beginning of fall, similar to what we saw in this picture right here. But then we always observe that as we go deeper down in the core that we no longer see layers that are that high. And the reason for that is that these top layers, those are preserved when we drill the core from the most recent year. But then with the melting that happens over the summer, we get degradation of the signal. So meltwater starts to move through the glacier. Some of that dust either gets removed or it gets reworked and can get moved and migrated within the core. So that's just to point out that using these cores to reconstruct higher amounts of or longer term periods of dust deposition is really tricky because you've got to account for those post-depositional processes that are happening. And another factor is that we can use satellite imagery to help us constrain this now. But when we're going into these sites and we're drilling these cores, it's not always apparent if that layer that we are sampling from the prior season is representative of just 1 year, or if it's possible that we've gotten consolidation of multiple summer layers into one. And so here on Drawn Brain, that kind of makes the point here that in 2023, peak concentrations were around 100 micrograms per gram, whereas when we were there in 2025, where we drilled, we had a concentration of up to 389, suggesting that we may have gotten consolidation of multiple years there. And we're going to go back. One of my graduate students has an Arctic field grant for the spring that will be doing a grid of 9 cores on the same glacier to be able to get at answering some of that spatial variability and post-depositional processes. So the point on this slide is just once again that the geology is quite diverse across Svalbard. So there's some areas that are much more characterized by sedimentary rocks, where you can have a lot more erosion, and the local outcrops can be greater sources of dust, versus some areas where you've got more metamorphic rocks that are harder to weather. And those pictures on the right are just showing differences in what we've observed by being in the field of how different that dust can really be optically depending upon where you are. So this is so the work that we did with the scanning electron microscope and with the X-ray diffraction was to look at how variable the actual dust composition is. And I'll just say the main points on these 2 slides is that we see some consistency in the dust in terms of the presence of certain rock forming minerals, or minerals that are coming from rocks, but that we do see some differences. So particularly in this region here in the central part of Svalbard, we see a larger presence of carbonates. And then this is the results of the XRD work that we did. And so once again, all of the samples contain abundant sheet silicates and common rock forming minerals, but that we just see carbonates present in certain areas. And then, as others today have spoken about, and as I mentioned earlier in this talk, one of the major things that we're interested in is looking at how these light absorbing particles are contributing to snow darkening, so albedo reductions, increased radiative forcing, and ultimately to glacier melt. And so a lot of the work has been done focused on black carbon. And so this is just showing if we model just for clean snow, or if we model just using for black carbon, and these are constrained by values that we've measured and also by peak values that are available in some of the literature. And so black carbon is lowering the albedo, but if you compare it to what we observe from the albedo reductions from dust, the black carbon contributions on Svalbard are relatively modest. And so this is showing each of these next 3 lines are showing different scenarios for if we only model for black carbon, if we only model for dust, and if we model for both the black carbon and for the dust. And in all of the scenarios, it really is the dust that is driving the albedo reductions. So black carbon has a much smaller effect, particularly when you consider how much dust is present. Drawn Brain, which is one of those sites that's is surrounded by a lot of dusty valleys, has the peak albedo reductions with broadband albedo 20% lower than clean snow. And so this reflects more extensive dust sources in this region, and that's consistent with spatial variability in regional dust inputs. And then, yeah, Biagio did this work, so it's nice that he's on the call today. So my intention is to collaborate with him further so that we can take the point measurements that we're working with from the glaciers to be able to extrapolate those measurements using satellite imagery to a larger area across Svalbard, so we can really start to look at how these light absorbing particles, particularly dust, are driving snow and glacier melt there. In summary, this research is responding to the urgent need to understand how climate change is altering dust emissions and their impacts on the Arctic cryosphere. This is providing us our first reported measurements of dust concentrations and dust deposition rates on Svalbard glaciers, and then provide some new analyses of dust mineral composition. And that while most of the research is focused on black carbon, our results show that dust is considerably more effective at lowering snow albedo due to its greater abundance. And so when we consider the changes that are happening with decreased snow cover duration, glacier retreat, and rising temperatures, we expect to see enhanced Arctic dust sources and emissions. And so with increased dust activity, our findings suggest that accelerated albedo reductions could be expected from dust deposition in the Arctic. Where we're going with this is we have a number of new cores that we've collected and hope to collect at least 2 more this spring. And we want to get more so at actually quantifying the radiative forcing and the contribution of the light absorbing particles to snow and glacier melt. So we've got the 4 new cores that we collected last winter. We did some processing of those at the Norwegian Polar Institute this past December, and those will get shipped to my lab in the US soon. And then we'll be returning to collect hopefully 2 more cores this spring. And then this kind of follows on the points that were made earlier in the session, that in addition to dust concentration and looking at the mineral composition, we also want to be able to be looking at the dust size and the dust optical properties, because those are really important for actually constraining how much darkening is happening from that dust in regards to snow albedo. And then, yes, I just want to acknowledge here our funding partners. The Norwegian Research Council has provided a lot of the funding for this, the US National Science Foundation and the Fulbright Foundation. So with that, I can take any questions if there are any.
Thank you. This quite interesting presentation and actual problem of darkening. Any questions from?
We have no questions in the room, if I see correctly, so we can proceed to the online followers. So maybe Santiago was the first, or yes?
Yeah, 2 questions actually. One is the one I put in online is I'm intrigued by the plot where you showed 2 successive core concentrations cores where you showed that the ear how the melting removes a lot of particles from the previous ear, which was an interesting piece of information. I wonder that phenomenon of melting and removing particles in the fern, does it happen in the underlying layers? So past years keep being impacted by melting and having particles removed?
In terms of, do you mean if it, like, let's say we had meltwater this year, if it could be affecting many layers deeper in the core continuously?
Correct. Yeah.
Yeah, I don't have a really good sense of that yet. So this spring, the Arctic field grant that my grad student has will be to collect a grid of 9 cores off of a glacier, and we'll aim to collect at least the last 2 layers. So that will be able to look at like this the spatial variability and what was there last year, but then also be able to look at least that layer down below. So 2 years ago and how variable that is. And then we do have 4 years of 10-meter cores that have been collected from that same glacier. And so there's just more work that we need to do in terms of lining all of those up and trying to understand more what's happening with the processes. But when I first approached this work, I was definitely wanting to use these cores to reconstruct, temporal deposition over time. And I think what we're learning is that those post-depositional processes are really causing a lot more altercation of the signal than we originally thought.
Yeah, I know that's I'm curious about because I mean if you 1 year you determine that in 2010 there was some level of deposition and then the 2 years later you come in and measure to 2010 again and you find that there is less deposition.
I'm just going to ask somebody a question in
Yeah.
a meeting here, okay?
No, it's not
Oh,
recording. I'll
sorry.
just, I'll talk, I'll
Anyways,
email you a
that's
message.
yeah.
Okay,
Good. Um,
Yeah.
I wonder, Norm O'Neill
Yeah.
in Canada, Sherbrooke, Quebec. I wonder what your feeling is about what kind of information can be extracted from reflectance signals, reflectance imagery from a satellite, and I also wonder there's a reflectance device at New Olison. If you've been in contact with Vito Vitali there, who's making, I guess, making regular reflectance measurements in different conditions.
So initially, when I first started doing the work there, we were measuring reflectivity, measuring albedo when we were going into the field. Because we're there during the springtime, that's not really what I'm most interested in. So the glaciers are most accessible during the period around April, because we can snowmobile and get to the sites very easily. But the concentrations of what's there is very low, and so what we were actually measuring ended up not being so interesting from that perspective. I think what's much more interesting, and I think Biagio is potentially better equipped to answer this because he does a lot more of the remote sensing work, is what we're able to do by satellite when we can actually look at when those dust concentrations are highest at the end of the spring. Santiago, I don't think I quite got to finish what you were asking, so perhaps we could circle back, or if Biagio is online, I'm not sure if he would want to chime in to address the satellite question.
Okay. Hi, Susan, and hello, everyone. So yes, there is the possibility to use spectral indices or invert sneaker or biosneaker model in order to get not only the concentration of dust on the ground on snow, but also the radiative forcing modeling the incoming radiation. So the next step for this will be to try to look at time series of concentration estimates and radiative forcing estimates and compare with what Susan measured with ice core and with surface sampling analysis to try to widen this perspective and try to understand how much of the area is impacted by dust and try to put numbers on the map.
Any links with Vito Vitali or
Yeah, he's on my same institute. He's retired now, but I know that they have some instrument collecting continuous spectral albedo measurements next to Ny-Ålesund. But I think that area is not particularly affected by dust deposition because when there is snow on the ground, you cannot see the dust. Dust cannot be resuspended from the nearbys, and when dust can be resuspended from the nearby, you don't have snow anymore at the site. So the instrument is measuring the albedo of the soil. So that's why probably it's not the best site for like this continuous measurement for dust analysis. For snow, it's okay.
Okay, thank you.
Okay.
Okay. I think this is the end of the session.
Yes, thank you, Michko, for convening the session. And again, thank you all the speakers of this session. Now we have planned a break, but if you want to continue in the discussions, maybe you just feel free to go on. We just, at least in our room, we will only take coffee in the side room. So I just leave it up to you as you wish. But if not, the next session starts at 5 minutes past half, or maybe 10 minutes. Let's see how the coffee break goes because we are a little bit and shorter in the coffee now. But anyway, thank you very much, and we meet 5 or 10 after how, so in 15 minutes about 20. Thank you.